Thanks. Begin with a word of prayer. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students, this class. Just pray that you be with us today. Help us again, Lord, to glorify you as we study your creation. Lord, in your name I pray. Amen. Okay, so correct me if I'm wrong here. I know. Am I missing? Are there any squares missing? Does this seem on the level to you guys? This is what I got last time?
I think K minus M gamma squared is quantity squared.
Quantity squared, okay. Anything else? Because I'm about to invest about 5 minutes in calculating with this thing, so I want to make sure I start off on the right foot, yeah. You finding it, Luke? Can you double check for me? Yeah. I would check my book. Looks good? All right. Now, so what we did, right, was we supposed that we had a solution like, we used a complex technique, all right? But basically we found that the solution was a sum of sines and cosines, and I told you we can rewrite it as a single sine with a shifted angle, right, with a phase angle. And then this is clear, the coefficient of sine is the amplitude, right? Sine goes between plus or minus 1, and this constant, whatever it is, describes how big the particular solution is, right? Its amplitude. And that amplitude, actually, when you look at it, so here, the coefficient, so the idea is to consider a family of possible forces with the same fixed amplitude F naught, but possibly varying frequencies gamma. And the system is fixed as well, right? So there's a particular mass, damping coefficient, and spring constant. And the question is, what choice of gamma, with everything else remaining the same, gives you the largest amplitude response, right? So we worked it out. We got this amplitude. I would point out that this amplitude is a function, right, of gamma. So we can differentiate this to find the critical point, right? So like dA to gamma, what is that equal to? Well, F naught, right? Parentheses K minus M gamma squared plus B squared gamma squared. And let's see here, I really should say minus F naught over 2 to the minus 3/2 power, right? So this is all of this stuff to the minus 1/2 power. So differentiating gives me that to start with. Then the chain rule says I have to differentiate the inside, right? So that times 2 times K minus M gamma squared. But the chain rule again gives me a 2 gamma, and minus 2M gamma. I've just differentiated. So chain rule says I have to multiply by the derivative of the inside function. Here's the derivative of this piece of the inside function right there, right? And then the other piece, this guy, well, that's easier. That's just 2b squared plus 2b squared gamma, right? All right. Now, if this thing is 0, we're in trouble because that would be division by 0. That could be a critical point, right? But why can't that happen? Let's see, there's a common gamma here, isn't there? And there's also a 2. Let me pull that out. So I'm pulling this 2 here and this 2 here off. So that leaves me with gamma times minus 2m times k minus m gamma squared plus b squared, right? agree? If you disagree, I'd like to know it. Trying to be careful here, but there's a lot of moving parts. Now, so getting back to my question, no, that can't be 0. It's the sum of squares, right? And we're assuming, by the way, that k is non-zero, right? I guess you could hypothetically have, if b was 0, right? Think about this. If b was equal to 0 and k was equal to m gamma, then you'd be in trouble, right? This solution would have trouble there. But that's not possible because we're assuming we're in the underdamped case where 0 is less than b squared minus 4mk. So, well, anyway, we are assuming that, that b is not equal to 0, okay? I'm not sure how clearly that's been stated. I may have stated that wrong. You had something different in your notes, and I probably should have stuck with it. What was yours? 0 less than b squared less than 4mk. So this says that b is not equal to 0 and 0 is less than 4mk minus b squared, right? Or, if you prefer, b squared minus 4mk is greater than 0, right? So the point is, if we did have b equals to 0 and k equals to m gamma squared, then we have division by 0. But that's exactly the case that we worked the other day where we had pure resonance. B equals to 0 brings us back to a simple harmonic oscillator, which is not the underdamped case. It's when you have no friction, you just get pure sines and cosines as your homogeneous solution. And that's the place where this particular solution is not legitimate. Because this, there you could have overlap precisely when gamma matches the natural frequency square root of k over m. And that's what we're seeing in this formula, is if b was 0 and this was 0, that's exactly when you match the natural frequency in the case that there was no friction. So we don't have to worry about that. That's outside of our consideration here. So this can't be 0, right? So we're trying to figure out when can this be either undefined or 0. That's a critical point for the derivative, right? That's where we know the maximum or minimum has to happen. So that's out. So we could have gamma equal to 0, right? Or what else could we have? Gamma equal to 0 makes dA to gamma 0, right? Or this could be 0, right? So that would be what? B squared equals to 2m times k minus m gamma squared. I think we're interested in what gamma, right? That's ultimately the question, is what gamma makes the maximum amplitude. So solve for gamma. What do we get? B squared equals 2mk minus 2m squared gamma squared, which gives me 2m squared gamma squared equals to b squared, 2mk minus minus b squared. So gamma squared is equal to 2mk over 2m squared minus b squared over 2m squared. Worked myself into the, we'll come back up here. So gamma squared is equal to, looks like k over m, right? Minus b squared over 2m squared. So gamma is equal to the square root of k over m, because we're thinking of gamma as a frequency, right? So, I mean, minus gamma and gamma actually give you the same formula here, right? Because cosine's even. So really limit our consideration to non-negative frequencies, angular frequencies, I suppose. And there you go. This is the so-called critical frequency, right? Angular frequency, of course, this is in radians per second, but Somebody have their book? No? I guess I'll check my laptop. Just give me a second here. I remember that the K over M should be there. Yeah? Oh, you got it. Yay! Save me the trouble. Thank you. Eventually I'm going to, well, maybe I won't. If you're bringing it, I don't have to bring it. Thank you. So we're in 4.9, right? And, or are we? No. Where's this stupid thing? He calls it not A of gamma, he calls it M of gamma. And so the calculation I'm going through right now is on page 223. And yes, he in fact does derive that either get gamma equal to 0 or the resonant frequency, he calls it not critical, but resonant frequency, square root of k over m minus b squared over 2m squared. Yeah, that's what we got. So, and if you plug that back in, so if you actually plug that in, so this is he calls it R for resonant, right? If you calculate the amplitude of the resonant frequency, what's that give you? So what happens if you plug that back into here? I don't know. To me, that's less interesting than what we just did. But you could work it out, right? He has a formula. I'm just going to copy it down, if you don't mind. So he says it works out to, oh, wait a minute. Well, there's no, his M is a little bit different than my A. Oh, his the relation between his M and my A's is the following. A of gamma is equal to F naught M of gamma. So that's the relation between the M and the A. I didn't feel the need to create something without the force in it. Excuse me. Anyway, it's just an exercise in algebra to plug this into there and see what happens. Of course, think if we were smarter, we could say that this condition is easier to work with, right? So this gives me what? K minus M gamma squared equals to what? So you solve this for K, multiply by M, right? Multiply this by M. Or go back over here where he had it before, I guess. Anyway, so K minus M gamma squared is equal to what? Looks to me like B squared over 2M, right? And so I can plug that into here directly. Square root of what? B squared over 2M squared plus, B squared gamma squared. Oh, goodness gracious. B squared gamma squared is that stuff. I don't know why I'm doing this, guys. It's not that interesting. I guess it's inertia. I started. And anything nice happen here? I've got two of these guys, eh? So this gives me a minus 1/2. Here I have a plus 1/4, right? So it looks like I've got the square root of b squared k over m minus b squared over 4m squared. And so you can factor the b out here, right? So there's a b squared right here and here. So I can factor that out to b times the square root of k over m minus 1 over 4m squared, I suppose. Now I'm worried to look at the book. I think you are correct. So I said I've neglected a copy of b squared in here somewhere. Let's see here. Where was it? this would give me b to the fourth, right? So there's a b. This is b to the fourth over 4m squared, right? And over here we have minus b to the fourth over 2m squared. So in total, that should give me minus b to the fourth, thank you, which puts a b squared here. And there you go, that's the book's answer. I guess it's somewhat satisfying. Well, I don't know what's satisfying about this formula, but here's a formula. This gives you the amplitude at the resonant frequency. Now, there's a possibility here, right? It could be, right? Possibility. There is a possibility here I should mention. We could have that k over m, right? Minus b squared over 2m squared is what? I could have the possibility that that is less than 0, right? So then gamma equals to 0 gives you the maximum in that case. Or is it the minimum? Well, at 0, it's a constant force. It's a constant force. But I think this is, well, I know this is possible. I've assigned problems in previous semesters, asked them to find the resonant frequency, and had the misfortune of choosing a spring system that had this. And then they figured out that the so-called DC force, like the constant force, is actually the place where you get the maximum response. So he has some pictures of these things in the section 4.9. See here, frequency response curves for various values of b. Anyway, I'm gonna shut up about this. There you go. That's. Excuse me. Goodness gracious. So let's go back to talking about the different cases here. Any questions about this? Okay, so if you look at this, we have characteristic equation what? We have m lambda squared, right, plus b lambda plus k equals to 0. That's the characteristic equation for this problem. So if we complete the square on this, what do you get? You get, see, well, let me just get to the point. Use the quadratic equation. What is the solution? You guys know quadratic equations. We can use that. Minus b plus or minus the square root of what? B squared, right? Minus 4 times AC, which in this case is mk, right? All divided by 2m, right? This is true in all cases with the proper interpretation, right? So there are different cases. If we have b squared minus 4mk greater than 0, right? What? Hey. Oh, yeah. Sorry, I'm an idiot. We're in the underdamped case. I was like, I wanted it to be different than what I have in purple above, but it wasn't different. It was like weirding me out, but that's just because I'm an idiot and I've forgotten that this is the underdamped case. Okay? So-called underdamping. So in this case, the homogeneous solution looks like what? Y equals to C1 e to the, minus lambda plus t plus C2 e to the minus, e to the lambda, lambda plus lambda. Sorry, I'll get it eventually. lambda plus t, lambda minus t, where lambda plus and minus are the obvious things, right? This is lambda plus minus. By the way, both lambda plus and lambda minus are less than 0. It's kind of easy to see that. First of all, if you have the minus, it's clearly negative, right? You guys agree? If I have minus, I've got minus something positive to subtract the thing negative. But what about plus? When you're adding a positive thing, you might worry that this is bigger than that, right? So it wins. But it can't win, can it? Because this is b squared minus something. So think about how that is, right? This would be, if this is 5, this is 25 minus something, right? The square root of 25 minus something is definitely smaller than 5. Right? So you're taking away what would match b. If it was just b squared there on its lonesome, we'd get 0, right? But then we're subtracting something that's positive, so this is clearly less than b in absolute value. So that's also negative. So they're both negative, which is to say that after a while, friction takes away the energy of the system, right? And the spring, it vibrates to 0. The other case, right, would be when the discriminant b squared minus 4mk is equal to 0, right? There you have lambda plus is equal to lambda minus, right? So you have lambda plus equal to lambda minus, and they're both equal to minus b over 2m, right? Then when the discriminant is 0, you just have a repeated root of minus b over 2m in this case. And so the solution actually would look like y equals to, c1 e to the lambda t plus c2 t e to the lambda t, where, again, this is the lambda up here, right? This is called what? This is called critically damped. All right? Aw, man. Is that underdamped? I'm sorry, all of a sudden, I get away from this terminology, I lose track of it. Let's see here, underdamped or oscillatory. So that's actually b squared greater than, critically damped I've got right. I'm not sure about the underdamped at the moment. He says b squared less than 4mk. That's not this case, is it? This is actually what? Yeah, this is actually the overdamped. Me being a Trump supporter and all, you'd think I'd be better at name calling. Let's see here. Overdamped. Sorry. Is it too soon? So this is overdamped. I'm an idiot. Critically damped is there. So now I'm like, see, it doesn't matter, right? The derivation, the whole thing we did the last hour of class or so, right? Finding the particular solution. All that really matters to make that solution, like the particular solution, legitimate, is that the particular solution doesn't overlap with the homogeneous solution, right? Where does the homogeneous solution behave as a pure cosine is in the simple harmonic case, which is when b is equal to 0, right? So that's like the simple harmonic is a special case of weakly or what's he call it? Some people call it weakly damped or underdamped. Underdamped is the third case. So I'm not sure. You see, it doesn't change anything. That's why you didn't notice it. But let me just erase that before it does any more harm to us. All right. All of these terms are stated in section 4.8, and if you're confused by me at the moment, I'm sorry. Don't be. It's really not complicated. There are three cases. They have three names, and I switched two of them. B squared minus 4mk less than 0. This is underdamped. All right. And what that means, right, if b squared minus 4mk is less than 0, that means that 4mk minus b squared is greater than 0, right? And so oh, I don't want to erase that. So let me call this case 1, case 2. I want to focus on case 3 for a bit here. So case 3, you notice we've got lambda minus b over 2m plus or minus the square root of b squared minus 4mk over 2m. It's that time of the day, isn't it? There we go. So there are only 4 people in this class now. Oh no. That means I'm only going to get paid 40%. I have to get to 10 people to get paid full for this class. Yeah, I love differential equations, so it doesn't matter to me. But if there were 2 people here, I'd still be teaching it because I love differential equations and I miss it. So anyway, so this is a negative number, right? So you can rewrite this as minus b over 2m, right? Plus or minus the square root of minus 1, which we'll call I, right? And then the square root of 4mk minus b squared over 2m. Or if you want to bring the 2m inside, we have minus b over 2m, right? Plus or minus I times the square root of what is this when we bring the 2m inside? When you bring 2m inside the square root, you get division by 4m squared, right? So 4mk minus b squared over 4m squared. Let's see, the 4's cancel, and we get what? K over m, right? Minus b squared over 4m squared. And so that's why he wanted to be in the underdamped case, is to make an interesting statement about the relation between the resonant frequency and the so-called natural frequency. Technically, it's not a frequency. This is the so-called quasi frequency of the system. Why is it a quasi frequency? Here, let me write the solution. The solution in this case 3 is what? Y equals to c1 e to the minus b over 2m. And if you don't mind, I'm going to write it as a single sine of, let's say, t times the square root of k over m minus b squared over 4m squared plus some phase angle. That's just a snazzy way of writing a sine and a cosine at once, right? We can either write a sum of sine and cosines times exponentials, or you can just write one sine with a shifted phase. If you do the adding angles formula for sine, this pops out like sine cosine phi plus cosine of the t times this root plus cosine phi. And so this breaks into a sum of sine and cosine with that t times the square root. So it's an easier thing to analyze because you can graph that, right? So this is the general solution of the homogeneous problem in the underdamped case. And the reason that's called a quasi-frequency, what's a frequency? What does it mean for a function to be periodic? Right, so f of t plus the period, right, is equal to f of t for all time, right? For all t in the domain of the function. If it's a periodic function, it should have this pattern. Like you said, it repeats. It exactly repeats, right? It doesn't sort of repeat. This sort of repeats in the following sense. There's this exponential. So this is sort of the amplitude. In the front, this is behaving as like A, let's say, quote unquote. It's the amplitude, but the amplitude isn't fixed, right? It has a time dependence. I'm missing a very important thing here. You guys got to stop me. What am I missing? Come on. There's a t missing here, yeah. Right. For example, if I had lambda equals to minus 2 plus I, my solutions would be like y equals to e to the minus 2t sine of t plus some phase angle, to give a specific example. Right? So I'm missing that. Now that gives me this envelope, right? Because that's an exponential function. And so it's, it starts out whatever it is. C1 is its max. At the time 0, it's at C1, right? And then that goes like that. And likewise, it's helpful to draw this down here, like that, right? And what does sine do? Well, you start out at sine of phi. When you plug in 0, we get sine of phi, whatever that is, right? That's our starting point. And then it waves. Right? So it's not periodic. It never returns to where it was before. Well, I mean, that's not entirely I guess it does. It returns to 0 a bunch of times, but it never gets this large again, right? It's that large at the start, never again. So it's not really periodic. So we shouldn't say that it has a frequency. It has a quasi-frequency. It's like a frequency. We know what we're talking about. We know what we mean, but it's not exactly a frequency. I think I asked you, excuse me. Goodness gracious. I think I asked you guys a question about quasi-frequency, so I wanted to talk about it a little bit with you guys. It's not a complicated idea, but there it is. So you notice the relation between the quasi-frequency and the critical frequency, the resonant frequency, right? They're very close, but they're not the same, are they? You notice the difference? 4 versus 2. So let's see here. That means that the resonant frequency is what? Is it smaller, or how do the quasi-frequency? Let's say, I don't know what that. Well, he has a name for that. I'm sure. I wondered if he had a symbol for it. He calls it the quasi-frequency. Oh, he's got no symbol for it. I was hoping for a proper name calling, but I got nothing. Anyway. One is smaller than the other, right? Like, here I'm subtracting a half of b squared over m squared. Here I'm subtracting a fourth, right? So it looks to me like this is a lower frequency. This is a higher frequency, right? For what it's worth. A question, or?
I was just curious if
Oh, the phi. Yeah, let's talk about that. So, generically speaking, our solution looks something like y equals 2. If I have lambda equals to alpha plus or minus I beta, right? If that's the case, then generically, our initial attack at this was that was e to the alpha t cosine beta t, right? Plus c2 e to the alpha t sine beta t. So what I'd point out here is you can factor e to the alpha t out, right? And then you get like c1 cosine beta t plus c2 sine beta t. But then, it's most easy for me to jump and then work backwards in my explanation. But turns out you can rewrite this as just the sine of beta t plus some phase angle. Or you could write it, or you could also write it as e to the alpha t cosine beta t. You got choices. Many flavor choices. There are other things you could do. Now, the relation between the C1 and the C2, and I'm missing an amplitude factor, all right? A. I do think it's the same A. Yeah. Well, I'm not sure about that. Well, anyway. This is what? This is sine beta t cosine phi plus cosine beta t sine phi, right? This over here, cosine beta t cosine phi minus sine beta t sine phi. So comparing, you see that, I mean, we can choose an angle such that whatever C1 is, right, C1 matches, C1 has to be this thing, right? And C2 has to be that thing, right? And you can always select a C1 and C2 to make it so. Well, that's not entirely true. There's A times, I should, to be more careful, sorry. A times cosine phi should be C2. A times sine phi should be C1. We can select an angle and an amplitude to make this go. We worked out last time, so sine squared plus cosine squared, right? Sine squared plus cosine squared is 1. So that tells me the relation between C1, C2, and A is that C1 squared plus C2 squared is A squared. And then beyond that, you just kind of have to do your usual 4-quadrant trigonometry to pick the angle. It's the same problem as finding a standard angle of a vector in 2 dimensions. There's cases to consider. I could write something like, tangent phi is equal to C1 over C2, but of course this must be used with care, because the inverse tangent only makes sense in quadrants 1 and 4, and in 2 and 3, it's a lie. There is no inverse tangent, at least in your calculator, Now, the story for the phase angle, this is not the same phase angle. I should say like delta or something over here, right? To be careful. These are not the same angles. All right. And so over there for the cosine, you'd need like a cosine delta is C1, and a sine minus a sine delta is C2. Again, a squared would be C1 squared plus C2 squared, but the way you choose the angle would be different, right? How are sine and cosine related? While we're on this nostalgia tour of trigonometry. How can I rewrite sine as cosine? Look at the graphs, right? Here's sine. What's cosine? This guy, right? I'm bad at this. So forth, all right? So basically, cosine is what? It's sine shifted pi over 2, right? So if you shift a graph, if I want to take f of x and shift it pi over 2 that way, I just look at f of x minus pi over 2, right? So that tells me that by transformations of graph, cosine of x is equal to the sine of x minus pi over 2. Again, you can check me on this. If you do sine x cosine of minus pi over 2 plus cosine x times sine of minus pi over 2, I think you'll find out I'm wrong. Excuse me. What's my mistake? I see it from checking my answer that I'm wrong. It's the backwards thing, right? If I shift to the left, the transformation of the graph, if you mess with the domain variable, it's like counterintuitive, right? So shifting to the left means you add. So I'm supposed to have plus pi over 2. Of course, you could have checked my formula by just plugging in like 0, right? 0, cosine of 0 is 1, and I should have 1 over here too. Sine of pi over 2, 1. Good, there it is. There's the relation. So as you compare like these two formulas, the sine of beta t plus phi versus the cosine of beta t plus delta, the relation between phi and delta is what? Whatever's in the cosine has to be whatever's in the sine plus pi over 2, right? Like that's the pattern. So this is so-called x, right? That makes this x plus pi over 2, am I right? So if you set those equal, you see that you've got phi plus pi over 2, right? Oh, excuse me. Oh, I can't do math. I guess I'm just going to solve for x for the sake of discussion. X is beta t plus delta, but over here x is equal to, so to get x here I'd have to take equal to beta t plus phi minus pi over 2, right? To solve for x there. If this is equal to x plus pi over 2, solving for x gives me beta t plus phi minus pi over 2. You cancel these, right? And there you go, there's the relation. Delta is equal to phi minus pi over 2. There's the relation between the angles, the phase angles for sine and cosine. They're different by 90 degrees. These things are important as you use like study phasor analysis and things, right? Because sometimes you want to write something in terms of sines, sometimes you want to write in terms of cosines. You can go from one formulation to another by changing the phase angle at the start. Anyway, I'll shut up. I probably said too much or not enough. I'm not sure which. Anyway, there is just 3 cases: overdamped, critically damped, underdamped, right? Now, did you guys got what you need? Give me a second. We good? Okay. So let's look at an RLC circuit for a second here. Suppose you've got, some voltage source, and then a resistor, a capacitor, an inductor. So Kirchhoff's voltage law tells you that the voltage source has to be matched by the current times the resistance, all right, plus the charge divided by the capacitance. That's the voltage on the capacitor. And then the voltage on the inductor is proportional to the rate of change of the current according to L di dt. All right, so get rid of this mess. So if you look at this, right, the thing is, I is the change in charge per time, right? So this Kirchhoff's voltage law, or KVL as it's sometimes called, you can rewrite that, right, as the voltage is equal to dq dt times R plus Q over C equals to plus L d squared Q dt squared. Or in other words, let me just rewrite it one more time. That's L Q prime prime plus R Q prime plus 1 over C times Q equals to the voltage applied. Now if you look at this, right? This is sort of the analog of Newton's law, Newton's second law for a circuit, right? It's playing the same role. And if you compare that, right, up to here, to say the spring mass force problem, what's the connection between these two worlds? You see that the inductance, right, mass is interchangeable with inductance. The damping coefficient, right, is interchangeable with resistance. And the capacitance is related to the spring constant inversely. So if I look at a circuit, so it makes sense to talk about circuits being overdamped, critically damped, or underdamped in the same way. Same mathematics, and you just change Y to Q. It's the charge flowing in the circuit at time t, right? And the same derivation we did goes through, and you can talk about what's the resonant frequency. Just for kicks, what would the resonant frequency here be in the underdamped case, which is, what would underdamped actually look like here? So I want R squared minus 4L over C, right? Less than 0, I believe. That's the discriminant. So that would be the underdamped case. And in that case, we could go through the same calculation we did, and we define the resonant frequency would be what? Square root K is 1 over C, right? So that actually, M is L, right? So that's 1 over LC minus, excuse me, B squared is R squared. And M is L again, so over 2L squared. And there you go. That's the, if you choose this to be, like whatever voltage V naught times the cosine of gamma t, if you choose gamma equal to this, you'll get the maximum charge flowing as a function of time, long term, for that choice. Assuming, of course, that actually is a real number. Otherwise, you get the maximum from just, I guess, constant voltage. So, by the way, guys, if you just have, an inductor and a capacitor in a circuit like this, this is called a so-called LC tank, right? Let's think about that for a minute or two. So here's an LC tank. And so to make this fun, what we should do is we should imagine bringing in a 9-volt battery or whatever, all right, and you charge the capacitor up, all right? Suppose you open the switch, right? You charge the capacitor up so it's charged, right? Charge the plates up. Suppose that the initial voltage on C is, let's say, V naught. That could be 9 volts, whatever. Adding numbers won't make it make more sense. So if you'll forgive me if I don't. And then suppose that you do that, all right? And then at time equal to 0, t equals to just a little bit beyond 0, we close the switch. What happens then? Well, let's see. First of all, Newton's law, so to speak here, Kirchhoff's voltage law, which is really just conservation of energy, charge, so forth. says the sum of the voltages must go to 0 in the circuit. So that here is just Q over C plus L di dt equals to 0. In other words, L Q prime prime plus Q over C is equal to 0, but I prefer to write that as Q prime prime plus 1 over LC Q equals to 0. So this is the case of a simple harmonic oscillator. There's no resistor in there to the resistor dissipates energy. It loses energy for the system. There's no resistor. We just keep going and going and going. That's why it's called an LC tank. It's like a tank. You put energy in it and it keeps it. All right. It's an idealization, but there. So this Q of t would be equal to something like Q naught, the sine of 1 over the square root of LC times t plus some phase angle. Phi. I guess I shouldn't say. I mean, Q naught may not be the initial charge. Well, anyway, it's some constant. Let me say C1. Now, do you guys understand the math that I just did going from here to here? Let me unwrap it for you. I've worked myself out of room, but I guess I don't need the... Oh, I was going to point out to you guys, the significance is 1 over LC. That's the natural frequency. That's like what we just found over here. 1 over the square root of LC is the sort of natural frequency for this. Just like square root of K over M is the natural frequency for spring mass without damping. So we've got lambda squared plus 1 over LC, right, equals to 0. Solve that. We get lambda squared is equal to minus 1 over LC, right? So therefore lambda is plus or minus I divided by the square root of LC. And that's why I wrote this solution here. It's just a pure sine cosine solution. Now this one's a little bit tricky because we actually have to use some sort of like physical... This one I wouldn't ask on a test because you guys haven't had circuits. I don't expect to teach you all the circuits. I'm just trying to give you some exposure to it. This is for breadth, right? Maybe this will help you with physics 232 when you get there. Maybe not. I'm sorry, guys. So, what are the initial conditions here? How do inductors work? They resist an instantaneous change in current. All right? So, what's the current before? Like, what's the current flowing here at time, just a little bit before 0? It's 0, right? So, inductors resist an instantaneous change in current. That means that the current flowing just a smidgen of time after 0 is still 0. So, I have an initial condition that the current at time 0 is 0. By the way, that's the same as Q prime of 0 is equal to 0. The other initial condition I know, right, is that the initial charge, and the Q, by the way, is the charge on the capacitor. Q at time 0 is related to the voltage. What's the relation between voltage and capacitance? Voltage is capacitance over charge over capacitance. So Q of 0 is actually V naught times C. Because the initial voltage is V naught, that means that V naught times C is the amount of charge on the capacitor at time 0. And so there you go. Those are your initial conditions. Q prime of 0 is 0. So by the way, this says Q prime of 0 is, C1 over the square root of LC cosine of phi, right? So that tells me that C1 cosine phi is equal to 0. I can't have C1 equal to 0. So that means cosine of phi has to be 0. That tells me that phi is pi over 2. And then with Q of 0, well, Q of 0 is also C1 sine, it's C1 sine of phi, right? Plug in 0 here, you get C1 sine phi. But phi is pi over 2, we just learned that, so that's just C1. And C1 is equal to, by our talking over here, V naught C. So there you go. The charge as a function of time is V naught C times the sine of t over the square root of LC plus pi over 2. And that's an example of an LC tank problem with initial conditions. Now for the test, guys, I'm not going to test you on circuits, okay? I don't think that's fair. Sorry, Luke. You got plenty of other courses, don't worry. But I do want to talk about it, because otherwise it's not fair, Luke. But for the test, I'd like you to know the difference between underdamped, critically damped, weakly damped. I'd like to be able to talk about those things, right? I don't expect you to memorize the resonant frequency formula. That's nuts, right? But if I have, I might want you to be able to derive it. But if I do, that's a significant investment of time on the test, right? So it's a kind of unlikely event. But I wouldn't rule it out of the realm of possibilities. It's a reasonable but tedious calculation you could do. The primary emphasis of the test, of course, is just on the mathematical techniques that we've gone over and how to use them and solve them. I have some old tests I can show you guys, so I'll do that. Any questions about anything? All right. Meander on here. So those are our main applications. Spring mass problem with an external force, or Rlc circuit, same math. Radically different problems, right? Same math.
LC circuit will actually discharge the capacitor over time?
Oh, right, yeah. What happens after you close the switch is the charge flows, right? It builds up the magnetic field in the inductor up to a certain maximal point, right? And then the inductor discharges. As the inductor discharges, it charges the capacitor, and then we start over again, and it just keeps going back and forth and back and forth. But it's just like a spring. You know, a spring goes like this, and then like maximum compression, maximum extension, and then in the middle, it's got maximum kinetic velocity, kinetic energy to the right or to the left, right? So it hits the maximum kinetic energy 2 times in each cycle, and it hits the maximum potential energy 2 times in each cycle, but in a different sense, either through maximum compression or maximum extension. Same thing happens here in terms of you have the magnetic field developed like in one direction, or the other direction you have plus, 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 minus, 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 or you have minus, 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 plus, plus, plus. So there's also this like flip-flopping back and forth. There's really 4 stages, 4 extremes that you're cycling through in every period. Yeah, the current being maximum is like the velocity, yeah, being maximum, exactly. One other thing I should talk about here, because we have touched on this, is the problem of energy here. So we talked about the energy lemma the other day, right? The question is, what is the sort of energy here? If you take this, first of all, forget about that. Forget about that. Homogeneous problem. What's the energy here? If you take this and we multiply by y prime, I can rewrite this as m mv dv dt plus k dy dt, right? Oh, sorry. Oh my goodness, that's not good. All right, so, and this is equal to what? Minus bv squared. Do the same calculation I did the other day. This is ddt. Now I did it for a more generic force the other day. We just did it for like an arbitrary potential energy, but